We're on the top of page 18, beginning with kinetics. And kinetics deals with factors that influence the rate of reaction. The rate of a reaction is how fast the reaction proceeds. So rate, again, is how fast. It would be measured in moles per minute or moles per second of either reactant consumed or product formed. All right, in this case, there are 6 factors that you should keep in mind. First one being concentration or molarity. So let's say you go from a 2 molar concentration to a 5 molar concentration. That increase in concentration of reactants increases the number of collisions per second between the reactant particles and therefore increases the amount of product formed in a unit of time. All right, increasing temperature certainly will increase rate. Turns out if you go from 10 degrees Celsius to 20 degrees Celsius, every 10-degree rise in temperature doubles the rate. So as you go from 10 to 20, it would double, and then from 20 to 30 it would quadruple. Increasing pressure by decreasing the volume of the container comes in handy when you're talking about gases in a container with a movable piston, or with a movable top, which you could think as a piston. So as you change the volume, if there's less space, there'll be more collisions per second, and therefore you'd increase the rate. Note that you should have here for temperature is that an increase in temperature increases both collision frequency and effectiveness. The frequency is the number of collisions per second, and an effective collision is a collision that produces product. So the reason why it increases effectiveness is because the increased temperature provides thermal energy so that when the particles collide, they not only collide more frequently, but they also collide with greater force. All right, so that's a good thing to keep in mind. The frequency and the effectiveness. Okay, another factor that you can manipulate is particle size. If you decrease the particle size of reactants and thereby increase the surface area, that would increase the rate. The reason for that is because there'll be more contact or more collisions per second. So think of it this way. Why don't we draw a block of wood that would have 6 sides to it. Now, let's take that same block of wood and break it into smaller pieces. So in this case, we've multiplied the 6 by 4. Now we have 24 sides. We've increased the surface area, therefore. And if this were the case of wood burning, and to illustrate, let's make this circle here represent the oxygen that can come in contact with these 6 surfaces. In this case here, with the smaller particles, there'll be more contact between the oxygen and the surfaces, a great number of collisions per second, and therefore a faster rate. Another thing you could do is you could dissolve in solvent. The most common solvent, of course, is water. So reactions in which the reactants are salts, for example, in an aqueous solution are certainly the fastest, or if not salts, and acids or bases in aqueous solution. So watch out for the aqueous and the reactants. Those happen to be very, very fast reactions. In fact, they would say they're instantaneous. And another factor that we should mention, maybe you remember the mention of these in living environment, and that is the addition of a catalyst. All right. For now, let's just remember that a catalyst is a substance that speeds up a rate of a reaction by decreasing the energy of activation, which is the startup energy, and we'll speak about that in a second. One other thing I want to note here, I'm not sure if it fits really here at this point, maybe I should have mentioned it in bonding, but since we are talking about energy, whenever bonds are formed, energy is released, and when bonds are broken, energy is absorbed. That's a good thing to keep in mind. All right, let's continue on this page here, and let's talk about potential energy diagrams. Now, it'd be just below this. Remember, potential energy is stored energy. So in a chemical reaction, when we compare the energy that's stored in reactants to the energy that's stored in the products, as a result of that reaction, we have what is called a potential energy diagram. And you're probably familiar with these. At first, this looks like too much information, so let's divide into two parts. So this half here pertains to an exothermic reaction, and the right half pertains to an endothermic reaction. And so the first thing we want to note is, if A and B are the reactants and they produce C and D, the products, in an exothermic reaction, the reactants will contain more energy than the products. So this is where you would place the A and the B on that plateau, and the C and the D on this plateau in a potential energy diagram. So this interval here represents the potential energy of the reactants. This interval here represents potential energy of the products. You see that in this case, in the exothermic reaction, the reactants contain more energy stored in them than the products. And that's why in an exothermic reaction, as reactants produce products, energy is released to the surroundings. And that energy released would be equal to the difference in energy between the products and the reactants. And that's what this interval here is, called the delta H, or the heat of the reaction. All right, another interval you should note is this interval right here, which is the activation energy, the startup energy. And that would be your E of A, the energy of activation. And it's the energy that the reactants needs to be boosted with to reach the top of this hill here. At the top of this hill, we have neither reactant nor product. What we have is an intermediate state or transition state known as the activated complex. So think of the activated complex as the stuff at the top of the hill. Okay, and when the reactants are boosted to this point, then from there on, the reaction will proceed. All right, and as we had mentioned before, a catalyst is a substance that decreases the activation energy. And so it's easier to go from reactants to products because there's less of a barrier prohibiting, an energy barrier, which keeps the reactants from becoming products. So you're lowering that energy barrier, so it's easier to reach the product state. All right. So that's an exothermic reaction, and just again, there's a lot of details here, but just keep in mind, the exothermic, we end up lower. So maybe to draw that out, just simply put, keep this in mind for the exothermic. And then for the endothermic reaction, we have just the opposite. We have the potential energy of the reactants, in this case, H little r, is less than the potential energy of the products. So there's a net gain in energy in going from reactants to products. So think of an endothermic as just the opposite of an exothermic. In endothermic, energy is absorbed. So let's draw that as a mirror image to an exothermic. And again, the activation energy would have, the activation energy would be this interval here, which is much greater than the activation energy to the left here of an exothermic, which would make this reaction less likely to occur. But the catalyst in both cases would decrease the activation energy. Whether it's endo or exothermic, the catalyst would speed up the reaction. And again, you have an activated complex as before. And let's talk about now this thing about the delta H being negative in an exothermic reaction and why it's positive in an endothermic reaction. So there's an equation that you should know that relates the potential energy of the reactants and the products. So let's look at that. There's some space below here. that we could focus on. So, delta H, which is any delta represents a difference. Delta H is a difference in the H's. It's called the heat of reaction. The heat of reaction is the potential energy of the products minus the potential energy of the reactants. Now, in an exothermic reaction, since the reactants have more energy than the products, we're going to end up with a negative. It's going to be a smaller number minus a larger number. So, let's write that down here too. In an exothermic, in an exo reaction, since H R is greater than HP, since the reactants contain more energy than the products, delta H is negative. And that negative indicates energy that's released. Energy, of course, that's released to the surroundings. So in an exothermic, it is a negative delta H, and in an endothermic, there'd be a positive delta H. And we should look now at table I, which has a listing of the heats of reaction for different reactions. So let's look at that right now. Table I, and you can turn to table I in your reference table, because I want to point out the first reaction at the top of table I. That reaction is an exothermic reaction. And how do we know that? Well, look at the delta H column, because you couldn't tell from the reaction alone because there's no energy contained in that reaction. But when you look at the delta H column, you'll see the negative there. So negative again means exo. And this reaction, if you were to touch it, would feel hot because it's releasing energy to the surroundings, and since you are in the surroundings, you would absorb that energy. All right, so delta H is negative in an exothermic reaction. If it's negative in an exothermic reaction, then we could place that heat, if we wanted to, in the chemical equation itself. So the heat released, since it's being released from the reactants, would be placed on the product side. On the other hand, if you look at this equation towards the bottom of table I, which if you recall represents the dissolving of sodium chloride in water, notice the ions that split and the water being the solvent, you'd find that this reaction here, or this process, is endothermic, which means that it's going to feel cold because this process, as the dissolving of most solids, if you recall, I mentioned this in the solutions unit, is overall endothermic. So in this case, if you wanted to place the energy in the equation, the heat absorbed would be placed on the reactant side. So you'd see it here. Now a lot of people give this a double take. They say, how come it's negative here in table I, but positive here in the equation? Well, first of all, the agreement is that we have no negatives in chemical equations. All right, the way we indicate whether it's heat released or absorbed is by placing it either on the product side or the reactant side. So negative in table I means place it on the product side, the right side. And a positive in table I means place it on the left side, which is the reactant side. All right, you'll see most of the reactions in table I have a negative delta H, since nature does favor exothermics. Also, just in case you forget that, let me just point out to you in table I, at the bottom of table I, they have this note here. They tell you minus sign indicates an exothermic reaction, so you really can't forget. Okay? Now, of course, these are not all the chemical reactions known to man, but there's a good sampling here that you could work with. And a good part of this table is, if you'll notice, in Table I, the first 6 reactions all have something in common. Besides the fact that they're all exothermic, you'll see that they all contain some kind of carbon-hydrogen or carbon-hydrogen-oxygen compound combining with oxygen and then producing CO2 and water. And so these are all what we call combustion reactions, which is a fancy way of saying burning. And then the lower third, I would say, of Table I contains, if you'll notice, all of these equations contain water placed over the arrow. And these equations are dissolving equations. Okay, so you have burning and dissolving, and then you have, in the middle, a bunch of chemical equations for the formations of different compounds. And then finally, at the bottom of this table, I should say at the bottom of these notes, let's talk a little bit about what we mean by equilibrium and how it applies to 3 examples. Now the word equilibrium, as you can tell, means something is equal, right? But it doesn't mean everything is equal. Equilibrium means when we've reached a point in a system in which the rates of the opposite changes are occurring at the same speed and at the same time. So equilibrium means not equal amounts, but equal rates. Remember, rate is how fast. And because these opposite changes are occurring at the same speed and at the same time, as a result, we'll get constant concentrations. And concentrations is how much. So when a system has reached equilibrium, there'll be no observable change. It's going to look the same in terms of color. There won't be any change in temperature, pressure, etc. Everything will remain the same. It's going to appear that the system is dormant or dead or static, but in reality what's happening is that you have opposite changes, which we'll go over here in a second, occurring at the same speed and the same time. So that's why you see no change. For example, we mentioned this last time in the solutions unit. A saturated solution is at equilibrium. Well, how so? In a saturated solution, the rate of dissolving is equal to the rate of crystallizing. So as depicted here, that solid at the bottom of your beaker in a saturated solution, which typically that's what a saturated solution looks like. You have some solid at the bottom of the beaker, which gives you the appearance that it's doing nothing. But in actuality, what's happening is that for every little amount of solid that dissolves, an equal amount of solute, in this case, that becomes undissolved. So the rate of dissolving and crystallizing are equal, and so it appears that this mass at the bottom never changes. All right. The phase equilibrium situation would be something like when you would take a beaker of water, then you could cap that beaker of water, and so preventing it from all evaporating. And what will happen over time is the water level will go down, and then at some point the water level will remain the same. And the question is, well, why is that? Is it because it's no longer evaporating? Well, no, that's not the case. What's happening here is it's reached equilibrium between 2 opposite changes. And the opposite changes here are evaporation and condensation. So at this point, when you see no change in the water line, or the water level, what's happening here is that the rate at which it's evaporating, for every drop of water that evaporates, or liquid that evaporates, better said, it doesn't have to be water, an equal amount of vapor condenses. And that's why the water line or the liquid line remains the same. All right. And the chemical equilibrium situation has to do with a reversible reaction in which the forward and reverse rates are equal. So the very common reversible reaction is the one that involves the formation of ammonia from its elements. So to remind you of that. So N2 plus H2, in fact it's 3 H2s, is going to produce in the forward direction, forward would be to the right, NH3, 2NH3, which is your ammonia. And then your reverse direction would be to the left, towards the reactants. And so what we have here with these double arrows, what we're depicting is a reversible reaction. Now, when the rate of the forward and the reverse reaction are the same, then what you'll see is the system's going to look dead. I'm not saying that at equilibrium that the amount of reactants and products are the same. What I'm saying is, because the rates are equal in opposite directions, the concentrations will remain the same, not equal, not necessarily equal. Okay, so we've come to the bottom of equilibrium, which is the bottom again of page 18. And on the next page, we'll start discussing equilibrium a little bit further, because we need to discuss, now that a system has reached equilibrium, how we could shift that equilibrium point. So I'll see you there on page 19 in a second.